So I want to go over the combined cycle drawing that we went over in class. For those of you who were not able to make it in class, I wanted to just go over the details, and I also wanted to go over the Rankine and Brayton cycles, and I wanted to make sure that you guys all understand where I was coming from. Then it's a little tricky. So these are temperature and entropy diagrams, and they help explain the process of what a gas turbine or a other heat engine such as a steam turbine are doing. So for the Brayton cycle, it starts at 1 and compression happens in the compressor. At 2, combustion happens at the combustor, and then expansion or work happens. The lines here are theoretical. Actual are the solid lines. And at 4 is our exhaust. So that's what's happening in the gas turbine cycle. For the Rankine cycle, slightly different. 1 to 2 is work put in, and it's a vertical line into the feed pump. It's very small and sometimes not even considered when we're talking about the Rankine cycle because so little work is put in. And then in the economizer, there's a little more heat put into the Rankine cycle, which you can't see real well in here, but it'll extend the Rankine cycle out a little bit to give it a little more surface area. More surface area in this diagram will mean more net work, just like the Carnot cycle. The bigger the area, the more net work you are going to get. So then evaporation happens from this point, and then our superheater increases our efficiency at this point, and work output at the turbine occurs from 3 to 4. When we reheat it, the actual line actually comes out a little bit, and we get a little more efficiency, more surface area in our T&S diagram, and then it'll exhaust in the condenser. That'll be our heat sink. So when you compare these two together, the Rankine cycle is sometimes called a bottoming cycle and a combined cycle because the Rankine cycle will be underneath the Brayton cycle, and its starting point is basically the end point of the exhaust of the Brayton cycle. This temperature here on this diagram will be very similar to this temperature here on this diagram. So if you overlaid these, we can utilize that process in this cycle. So as said before, a combined cycle is 2 or more systems operating at different temperatures and sometimes different fluids. So here's a little bit better picture of this plant. This is an actual PNID, and it's color coded showing the process flow. I'm not going to make you remember all of these lines, but I do want you to recognize that our main steam is coming out of the top of the HP drum, and it's heated through several superheaters, and then it goes to our high pressure turbine. I also want you to recognize that this is an economizer. At this point, a feed water economizer. There are several economizers involved in here. I'm not going to make you remember what each of those are, but I'd like you to grasp that between the drums there are going to be economizers, and I'd also like you to know that the steam coming from the IP drum actually goes through a superheater, and then it comes out and it actually intersects with the cold reheat line and helps heat that line as it returns to the intermediate stages of the turbine. Also remember there's a LP superheated line that is used for efficiency at top loads. This item here is our condenser. Our LP steam is exhausted into our condenser. Our vacuum system comes off here, and our circ water, which is coming from cooling towers, is cooling our condenser. And then this is our condensate pump that will then go to our steam air ejector, which helps pull down the vacuum in our condenser. The next heat exchanger is our gland sealing exhauster, which pulls a vacuum from our steam turbine glands. And then there's a recirc pump here. It's easily seen right here. And then this is our first feed water economizer as it goes into the LP drum. So this is the same drawing again, just a little bit simpler for teaching. This is our stack. Our Sims equipment will be located here. This is our boiler feed pump. It has 8 stages, and 2 of the stages will deliver water to the IP drum, and then the last 4 stages will deliver water to the HP drum. The LP drum also acts as a de-aerator, as it's a storage tank. It's usually 6 times the size of these other 2 drums. Also, I failed to mention that this is usually run, the HP drum is run at like 1800 PSIG. This IP drums usually run about 1000 PSIG, and the LP drum is usually at about 80 PSIG. So there's quite a jump between the drums. This is our gas turbine. The exhaust flows this way. This is our compressor. This is the combustor where the fuel goes in, and this is the turbine. Here's our generator putting out about 170 megawatts. This is our air intake system. The air is drawn in through the compressor, and usually there's some power augmentation, such as evaporative cooling, which is basically a mist of cooling water that goes through here. So those are the basic components. We'll be seeing this again on our next exam on Friday.